Right.
Solve this crap for them. But a lot of times we forget about it too, and we get caught up in mismessaging. I mean, I had a lot of discussions at Cisco about it was something basic in the semantics about PIM and SSL.
Either way, that's why we decided to do this draft, because other non-multicast groups were asking it came up in the side meeting, like, what the heck is, what multicast protocols are being used? Why did you guys use the other ones before? It'd be sure nice to have a history lesson. Yeah.
That's why, I mean, like, people ask me those protocols, and I wouldn't necessarily like, that's every protocol, you may have a little site that's about them. But the story is like, why did these things get built where they were? Maybe you tried this and didn't work, or this was introduced. But remember when Pierre came to give a presentation on using dense mode for source discovery? No, not dense mode, excuse me. Vider for source discovery and SSM.
Excuse me for a second. Oh, we gotta get started. Let's get going. Quit taking your pictures.
It was like, dude, 15 years ago, this was great. Right? But today,
yeah, exactly. And the getting past it, we need to understand why we needed to get past it. So, yeah, I agree.
Neighbor.
Social stuff.
Yeah, forget the social stuff. Hit it. Start us off strong.
All right. Okay, I'll start. Okay. Yeah, can you bring up the slides?
Yeah.
Yeah. Welcome to IETF 117. Welcome to San Francisco. Now you've been here the whole week already. So yeah, let's get started here. Glad some of you made it here on a Friday. Okay, next slide. Yeah, you have hopefully seen the note well. So yeah, please keep that in mind. Next slide. This is our agenda. Any comments on the agenda? All right, next slide. So the working group status. So we have these DR documents that we really need to do something about. I see I accidentally say one of them is on the agenda today. That's copied from last IETF. Anyway, yeah, we need to do something about that. We published another Yang model. We also have a couple of drafts in the RFC editor's queue, so we are getting some work done. Then we have these BIS documents like IGMP, MLD, BIS, and we did a working group last call, but no one responded. It's complete silence. So yeah, we'll try to do another last call, and we need at least someone to respond for us to progress them, I think. And yeah, you all are pretty familiar with these protocols. The main thing is to check what we are changing, as we progress to BIS and whether those changes make sense. Okay. Let's see. Next slide.
So you're going to issue another working group last call?
Yeah, I think so. Yeah. Okay. Then we have these point-to-multipoint documents that are more or less ready for last call, I'm thinking. But yeah, we're not discussing them today. Also, PIM Lite is not discussed today. Then we have this John Prune Lisp extensions to PIM. That went to last call, but there were several comments there. I think the draft needs some major work before it can progress. Yeah, we adopted lessons learned since last IETF, and that will be presented today. And yeah, there's this 8736 BIS that also is in RFC editor's queue. I'm trying to remember what that is now. It's my document, but we just had to make some changes to the IANA language, I think. It was just a very minor change that was kind of important for process reasons. Okay, think we can go to the first, or any questions, comments? Okay, let's go to the first presentation, I think. Hmm. Oh. Mm, don't you? Is there a button like share document or something? Or... Right, and share your screen. Mm. All right, okay. Yeah.
Okay, so this draft was adopted recently. It's a draft that was also presented in MBOND this week to get some feedback from them. And it's a draft to provide some lessons learned on multicast over the last 30 years. There was feedback from a side meeting last summer about, what the heck is going on with multicast. We have a variety of protocols. Why aren't we using certain protocols anymore? Why do they get dismissed by people? And so this draft is to address that topic. So really, again, our purpose for this draft is to help us understand the previous development work that leads us to where we are today. And maybe this will help us understand ongoing efforts. We started with DVMRP because that's really how multicast started on the internet. We have this disinspector algorithm that's being used in a flood and prune manner to share routes, and we included some information about MBOND in this, about the multicast backbone in this latest draft. And so that's really where we start with the draft, is kind of talking more about DVMRP and how it doesn't scale that well today because of, or it quickly didn't scale because of the higher bit rates and the larger deployments of multicast. And then we get into IGMP version 1 and why we needed a version 2 and a version 3 and the importance of providing leaves and importance of being able to join certain sources. And then we discuss dense mode and sparse mode and all that. Next slide. These are the current topics that we are addressing. Next slide. And the final slide. So we did add BIDR per Lenny's request, and he's one of the authors. Did, as I mentioned, add a bit about MBONE as it relates to DVMRP. And this week, the MBONE participants suggested to include MSDP and session advertisement. So we will do so for the next IETF. We'll continue to evolve this draft. We'll probably be working on it for some time. We are working on major issues. Lessons learned. Don't plan to include all protocols, but we do include the major ones, I guess. And we appreciate the comments so far. We're trying to include them. And any comments? And I know Torres is in the queue, and now Greg also has some suggestions as well.
Hi, Todd Zecker. Early on in the document, I provided a bunch of proposed things that I felt would be useful. Did any of that make it into the document?
Not yet, but one thing that we did add that you brought up was the M-bone, and so we included that. We didn't really discuss that much, so we discussed that more. So we'll start including more from your.
Well, yeah, let me know whenever I can help on those topics.
Thank you.
Greg Shepard, breaking things. Here we go. NSRC route views. I'm just talking to a couple people about this one too. Like that, this problem comes up all the time. Mike. Okay, this problem comes up all the time, which is why the draft is coming up. And I think it just hit me now. This wasn't when I came into the mic for, but hit me talking here in Torless that in M-bone-D, people are also asking about other protocols. If we don't stick them all in, at least give them a section, these questions are going to keep coming up. The point of this draft is to stop this, or at least point them to a document now. We can say, there it is. We all share the same narrative at that point. So something to consider. Even the sideline stuff that happened, like why did that happen? Explain it. It might just be a paragraph, but we're done, right? It'd be nice to get a document that's complete. What I came to the mic for is say that I attempted this once before, if not more than once. In the beer BOF, we wrote a problem statement, and we also wrote the problem statement. In that, I wrote a narrative from Deering's epiphany to beer, and it goes through at least my view of how we did that transition. So it's an expired draft. I wanted it to get published because I wanted the story out there so we can point to something. But in the context of beer, the ADs didn't think this really fit as something to go forward working group doc. It belongs pure M-bone-D, really. So this doc is expired, but it's still accessible. It's draft IETF beer problem statement. Feel free to steal any or all of it or none, whatever you think fits. And if you want to roll me in to help put this together, I'm in.
Great, thank you. Sounds perfect.
I just wanted to say thanks for putting this together. It's really valuable for somebody who's just trying to learn about the different protocols out there and why we use some and not others. So thank you.
Yeah, thank you, Nate. Okay, great. Let's move along.
Yeah, great.
Hongji.
Hi, Mike. Can you hear me?
Yeah.
Okay. But I can't see your screen.
Yeah, we'll get there eventually. Hold on. Go ahead.
Okay. Good morning. I'm Hongji from Ericsson. Now let me introduce some updates about this EVPN multicast young model. Next, please. In the last year, we have got some comments about this draft, so we made about three updates about this draft. Next, please. Draft update 1, we changed the multicast source address from iNet IPv4 address to iNet IP address so that both IPv4 and IPv6 could be covered. Next, please. Update 2. we have changed the multicast group address from RTCAP's IPv4 multicast group address to IP multicast group address so that both IPv4 and IPv6 could be covered again. Next, please. Update 3, we changed the maximum response time from int 32 to int 16, and this is to keep consistent with the query max response time defined in the IGMP MLD YAML model. They both specify the maximum time allowed before sending a responding report. Next, please. This is the whole hierarchy about this YAML model. In this YAML model, we extend the IETF EVPN data so it includes the three new EVPN routes to carry the IGMP membership reports from type 6 to type from type 6 to type 8. They are the SMART route and the multicast membership report sync route and the multicast leave sync route. Okay. Next, please. Okay, that's all. We welcome any more comments. Thank you.
Yeah, this is Stig. So one question though. This is about EVPN, right? So have you presented this in BES, or are you trying to present it there?
On last IETF meeting, I have sent an email to the BES chair, but it wasn't placed on the agenda.
Right.
But I have reviewed the web page about the BES working group. I see that I saw that this draft has been set as a related draft in the BES web page.
Yeah, I think we need to talk to the best chairs, where the document fits, and if they agree it fits in best, then hopefully they can get it on the agenda.
Yeah, and we've tried actually. We just haven't got a response. So maybe we can have our local BES expert help us bridge that gap. Nakamana.
No, I mean, I'm not sure if the document itself would not be in PIM or BES, right? But given how it's adopted, I think we should be responsible for finishing it, right? I think the decision which group it is, I think it's too late, but just escalate the fact, right? I mean, it is about. It seems the status is that PIM is the best working group to do the Yang for these components of the particular service. The service is in BES, so it seems like it shouldn't be too hard to get the working group chairs to make sure that it does get appropriate review by the working group.
Right. Yeah, we might possibly do it here, but we need to make sure it at least gets reviewed by people at know EVPN.
AC Lindum Lavin. I, have been following BES, and they have a significant backlog of documents at every phase, including AD review, where he's pushing back and complaining about the quality of the documents coming to him for review. So it would be good to do it here if you could. Now, having said that, when you think about MBPN, the MVPN multicast, or EVPN multicast, it's more about the BGP encodings than it is about multicast. Really, you think about it. I mean, for the most part, you get that, because 6513 and 6513, 6514, those two, they were done in best. But if you could do it here and get review just as a matter of finishing it sooner, that would be the reason to keep it here. But if you're just looking purely at where it should go, I think it's more about MPBN and EVPN than it is about the base multicast capabilities. Thanks.
If we don't get a response from them, do you think it would be bad form just to issue an adoption call in this working group and just see where it ends up?
No, I don't think so.
Okay.
I mean, like I said, they have at every phase from documents they want to adopt to last call to ones waiting for AD review. They have a significant backlog.
Okay. I heard it got a little heated in there too, so I need to watch that video. All right. Let's do it. Yeah, it's up.
Yep.
Yeah, you're good.
Not on mic. It was just normal meetings during negotiations.
Oh, okay. Okay.
Yeah, hi, I'm Stig Vanas. Present this new draft that I wrote recently. So we have this PIM flooding mechanism and source discovery, which is an RFC from some years back, and started actually implementing that, and we found out that it's nice to have some extensions to that, which I'll talk about now. Next slide, please. So in 8364, there is a TLV for announcing a source. It's basically source address, group address, and hold time. And that's fine. But then we are thinking now that it can be useful to sometimes announce some additional data, like parameters or something about the flow, like bandwidth or flow, the rate, packet rate might be one example. Won't go too much into that, but if a router knows what the rate is of a flow, it can avoid joining an interface, the upstream interface, if there's not enough available bandwidth, or in case of ECMP, you can make some better decisions about where to join, for instance. But the main thing is, if you want to add some info about the flow, there's no easy way to do that with the existing TLV. And I'll explain that on the next slide. Next slide, please. So this is the TLV that is currently defined. So it's basically just group address, source address, and hold time. If you now have multiple of these TLVs in a packet, and you want to add some new TLVs, say about bandwidth, it's not that easy to say, if those are separate TLVs, how do you know which source group address goes with which bandwidth TLV, for instance? So the purpose here is to do new TLV. Next slide. So the idea here is to have sub TLVs. So basically, it's a new TLVs that can have sub TLVs, and that means that you can have the main TLV with the source and group address, but then you can have a lot of additional metadata or whatever about that flow if you want. And bandwidth is just one example. There could be other stuff that you might want to announce as well. Next slide. And for the flow rate sub TLV, I'm proposing the format you see here. There is an RFC from long back for, what's that called? A pop count. Dino knows that. And with pop count, I actually had the idea that you can, when you send a joint upstream, you can include some information. And one of them is I forget how this is used in pop count, but you specify the bandwidth you have available or the flow bandwidth or something, I'm not quite sure. But at least this format is exactly the same as in the pop count RFC. So it's just some fairly efficient way of encoding the flow rates.
You take questions?
Turles,
Sure.
Turles is in the queue. Go ahead.
My last slide. So, okay, Turles.
So was just we had this actually in running code in the end of the 90s with the SAP announcements, right?
Right,
So,
right.
you basically creating a weighted fair queue for anything that was an SAP and where you joined, where you're on the tree, to guarantee the bandwidth for the flow, relatively speaking, not absolutely. And so I'm wondering, you know, the more information we put in there, that's kind of also helpful for diagnostics, or so the less I feel that's a good thing for PIM. But why don't we simply use SAP and just revisit what were the criteria why we ultimately said we want to get rid of it? And but you know, there seems to be, you know, more diagnostics that don't really necessarily maybe best fit for PIM, and we had done SAP. So
Yeah, I know. I was thinking about that. I don't want to turn this into a new SAP kind of.
no, but I think maybe
but,
it's a draft on how to you add SAP to this existing feature.
Yeah.
What is the delta? What are you missing?
Yeah. No, it's interesting to consider. I agree. And so at least for this, I'm mainly thinking, you know, what information is useful to the routers to make decisions, or probably troubleshooting also. But don't want to put in too much, like, you know, sort of SDP has the more like human, or SAP, you know, interface, you know, information for like the end user as well.
Well, I think the main difference was, if I remember correctly, SAP was meant to discover the session, so it was on its own group.
Yeah.
And if we here now just say, you know, we want to give more information about the session to the session members, right? Then we just figure out how we put it on the same group, and that would be a change in SAP. But then it would, you wouldn't call it PIM. It would be
Right.
still, right. So something in that.
Okay, sure. Yeah. Okay. Thanks.
This is Dino. This might be a terrible idea, but you might want to make a sub-TLV encoding that says it's JSON formatted, and you could put ASCII JSON in there. We did this with Lisp, and everybody said it was a bad idea. I use it all the time. It's so flexible. Okay. Anyways, it could be, and it's gonna, then you're gonna have MTU size problems, but anyways.
The upgraded recommendation, of course, is called CBOR. That's the binary version of it, but you still are as flexible in specification.
Yeah, no, at least I would say the main thing is, you know, to get the TLV concept in there so that we can do all kinds of extensions if we want to. Yeah.
Hopefully the JSON is the last TLV you have to put in.
Right.
But it depends. There's a lot of objection to that.
Yeah, I'll think about that. Yeah. I think that's the last slide. Yeah.
Send it on ZTE. I think this idea may bring more idea. Maybe something, many of things like Dino said, many things will be inserted in this TLV. But I think that this has brought a way to convey many more information into the domain. So I think it might make sense, but I think we might discuss more about what we will put in the information.
Yeah, I'm certainly open to ideas. We could possibly define some more TLVs in here. Of course, we can also do future RFCs with new extensions.
Yeah.
I remember in the pop count, this is Dino. I remember in the pop count draft, Shep and I struggled quite a bit about merge points, and is information aggregated? Is that a good, it's aggregated for scale, but then it filters it for usefulness. So, you know, that's the big problem with putting it in joins and putting it upstream on a tree.
Yeah, and I kind of like this, you know, where the information comes from the source. It's kind of more natural in a way. Okay, yeah, thanks.
I got a quick question. So you are referencing RFC 8364, which is experimental.
Yeah.
Are you planning to make this, if this were to be adopted, is this something that would be experimental as well?
Yeah, I think it has to.
Okay.
Yeah, the other thing though is we have running code and and have done also testing of that RFC, so it could potentially be progressed to proposed standard, but ideally we should have maybe 2 implementations before we do it.
Do you want an adoption call or no?
Yeah, we can. It's going to be a little early. I don't know how many people read it.
I'm going to do a quick little poll. Sorry, I struggled on the question, but I think you get it. Okay, thanks. So we take minutes from the video later. So just for that sake, we have 9 in support of adopting this draft and 1 against. And we will take it to the list. Thanks. Okay. Ananya, PFN forward. We have that one. Yes. I think I got it. Is this? That's not it. Let's try it again. We had this one loaded, right?
Yeah, let's see what it did.
PIM scaling for multiple upstream.
It's uploaded.
It is uploaded. Yeah.
Hi, this is Ananya from Cisco. I'm a first-time presenter, and this is the first time this draft is being presented. Next slide. So like in the previous slide, in the previous presentation, Stick talked about the PIM flooding mechanism. So this is also one of the extensions that we can do to that experimental RFC. So today in PFM, between 2 routers, when they exchange PFM messages, these messages are flooded on all the links between them. So let's say these 2 routers have PIM enabled on these links between them. A PFM message that is intended for the other router, it goes on all 3 links, and obviously the other 2, the black links, they would just be dropped because of RPF checks. So this problem can be further optimized if 2 routers have multiple PIM enabled links with each other. Next slide. So the proposed solution for this problem is that we can also implement RFC 6395, which helps a router identify another PIM router on all the links. So basically, if it has multiple links with the same router, it can identify that these messages are coming from the same router, even though they are received on different links. This can be done with RFC 6395, where we exchange a router identifier as a PIM hello option. And the optimization for the PFM forwarding enhancement would be that if we see a router that is advertising this hello option, we can check on all the links if we are getting these messages from the same router. So if the same message is received on link 1, 2, and 3, we can say that this message is actually being received, being sent by the same router. Of course, we would need a new hello option, but it will only advertise a router's capability that it is able to optimize PFM messages. So if a router is advertising the router ID and this PFM optimization hello option, it can optimize PFM message exchange. So the way that we will do it is, the proposed solution for this is that if we can choose one link per PIM router pair, and we can ease the RPF check, we can relax the RPF check on the other box, given that both of them know that we support this optimization, as well as we have a unique router ID. So this would help in reducing the number of PFM messages that are being exchanged between two routers which have multiple PIM neighborships over different links. Any questions or comments?
Sunny Zhang ZTE. I think that from this solution, if all the nodes in the domain support this capability, I think it's a good idea, and all the duplicate packets will be disappeared. But if there is node don't support this capability in the domain, so I think the duplicate is still existed, right? So I think maybe we should consider how to make sure all the nodes in the domain can support this capability and we use it. Otherwise, I think it may have some disadvantage. Yeah. So that's my opinion. Yeah.
I think that test case is actually covered in the draft, but yes, I will look into it. Where if all nodes do not support it, how we should react, I have uploaded in the draft. Yeah.
This is Dino. To support that idea, should PFM have a capabilities message that, and the only requirement is everybody has to support PFM first, and then after that, any new capability in the future can use that mechanism? Don't know. And how often do you send these general PFM messages? That's, sorry.
Yeah, so yeah, I can comment to you as an offer. So yeah, at least what we currently say is we use, PIM hello to announce this capability.
To neighbors.
Yeah,
To-
yeah,
So
because,
not, she
right.
sending it throughout the
Yeah.
domain, right?
So, well, at least, yeah, at least the way I see it is this optimization can be useful even if it's on some routers. I don't think there's any harm in doing that. But to get full advantage of this, you would want all the routers to support it. But yeah, I have thought about this, and for my previous presentation, I mean the one I presented, the
Yes.
sub TLV, the problem there is if you want to use the new TLV definition, and then you don't know whether all the routers support the new TLV or not, right? And then, sorry, I don't know if you know what I mean, but
But you're right.
yeah, with my draft is like you're replacing the old TLV with a new TLV.
Yeah.
But that's bad if there's at least one router somewhere in the domain that doesn't support the new TLV. So then I have the problem that you were saying. It would be nice to have some kind of domain-wide knowledge of what the capabilities are.
And if
And
you do
PFM
have,
could
if
be
you do
used
have
for
the
that.
knowledge and
Yeah.
90% support the feature you want, can the feature be turned on? Is it an all or nothing?
Right.
It gets complicated, but
Yeah. Now I also had this idea that with PIM hellos, you can know if your neighbor supports something. You could maybe say, you flood this information with a new TLV, with a bandwidth and whatever. But then if along the way, if you find out, oh, I have a PIM neighbor that doesn't support the new TLV, can you translate the message, like replace it with the old TLV so the neighbor will actually understand it? Yeah, no, the new guy that supports both TLVs can replace the new with the old, so the other guy can actually get it. But it gets complex. So yeah, maybe we should think about some kind of domain-wide capability for PFM, and yeah, it could be, it's something you don't need to announce all that often. So yeah, we can think about that. And yeah.
And to answer your question about how often these messages are shared, it's upon source discovery, and they're also periodic. So if we do implement this, we can reduce the number of periodic messages sent over in the PIM domain.
Yeah. And yeah, if anyone is interested in working on a draft for PFM capabilities, that would be cool. But anyway, okay, thanks. Yeah, we should focus on this draft.
Hold on a second. So adoption call or no?
Yeah, what do you think?
Should we care?
Yeah,
You want me to get in the queue? I just have one question.
Just
sure. Yes, the main question is so many people haven't read it, but up to you if you want to do it or not.
AC Lyndon Lavin. Hey, it's been some time since I've looked at this in detail. So if you don't have this and there's PIM running on, say, all the parallel links, the data plane multicast packets will also go over all three. You need this to optimize the multicast flows as well, don't you, right?
Right.
Yeah, okay. It's not, I mean, you're not just optimizing the flooding of you're optimizing the actual, the more significant multicast flows.
No, this is just the announcements.
These are just control
yeah.
plane
Just the
packets.
announcements, but
Yeah.
okay, let's say you don't have this. And there's a flow and you're running PIM on all of them. Will it only select one, or will it go on all of them?
No, so
One way, okay.
So so you will pick a single interface to join the flow. Yeah, yeah. The only thing here is that you unnecessarily send additional messages and just do more processing. Yeah.
There's no pruning of these control messages. It's just like a dense mode with no flood, with no pruning.
They're sent on all links.
Yeah.
By the way, BSR has the same
thing.
Okay, so we just started an early adoption goal just to get an idea, because eventually I'm guessing we'll be taking this to the list. Same question I had for Stig. Is this intended experimental or standards track?
I think it has to be experimental because the main RFC is experimental.
So Stig says he thinks it needs to be experimental since the main RFC is experimental. I think the draft right now says standards track, just so you know. But okay, so right now we have 10 in support and none against. So thank you. All right, Torless, you're up. If I can find it. There we go.
All right. So this is hopefully one of the last ones of our documents to move our standard track set of protocols forward. Next slide. So quick reminder, REC 1112, kind of Bible of multicast, specifies IP multicast host stack, not the routing protocol. Also includes IGMP version 1, which is the primary issue because we would like to make IGMP version 1 historic, but we obviously don't want to make RFC 1112, the rest of the IP multicast host stack, historic, so that kind of raises the issue. And the idea with 1112 bis is to remove IGMP version 1 update the text accordingly with all the newest protocols, IGMP v2, v3, add also mentioning of IPv6, which was invented or got into the IETF standards track 10 years after 1112. So there is no mentioning of IPv6, so there is not even a real RFC specifying IP multicast for IPv6. And then we can also, of course, mention that we are now calling this ASM IP multicast versus SSM. So this is all what the draft already is doing. Last time we had two very useful feedbacks. Next slide. So Alvaro was concerned about us keeping the text as much unchanged as we could, which pretty much meant that, like a lot of documents pre-2008, there is no normative must and should. And Alvaro was worried about 8200, IPv6 itself having had a lot of trouble with that. Now, I'm not aware of 1112 having had any trouble with missing normative text. And so we've been 34 years around with this RFC. IPv6 only 6 years, so maybe, you know, multicast people are more agreeable with the RFCs we've written. However, I went through the text identifying the applicability of normative notion must should and changed those to the normative one. I think looks fairly simple, should be fine. Also added the normative language disclaimer text, of course. And I would think this should address Alvaro's concern. So we'll use the standards text. Right now, my logic was I'm applying the normative text to all the packet interface description, sending and receiving multicast packets. The need, of course, to support IGMP v2, v3, newest version, and MLD. I haven't used capitalized must and should, where it talks about the higher stack, the socket, the application facing elements, because we don't have history, but I'm open to do that. I'm only aware of a single working group who may have done that, so we can check with this. So, but yeah, so the must and should for the packet facing stuff, I think looks easy. Next slide. So issue 2 was from Dino. If we move 1112 and hence IGMP version 1 to historic, it wasn't clear from the text in version 1 of this draft what would then happen to IGMP v2 and v3 implementation. Should they all go back and remove IGMP v1 code and kind of recreate the biggest mess of multicast on the internet? That wasn't quite of my intention, right? But how do we make this perfectly clear? Of course, we don't want to change any of the existing implementation and also not any of future IGMP or IGMP v2, v3 implementations. We just want to avoid something we've seen even as little as several years ago, where their host implementation that just have IGMP v1 and they feel perfectly happy because, well, it's a full internet standard, right? So that's what we want to avoid. So how do we do that in the text? Next slide.
Do you want to take a question or not?
Sure.
It's just a quick data point. It's not a big deal. It'll be real quick. We just discovered this week that there's one OS that doesn't support IGP at all. So
Right.
they're pushing you to IPv6 multicast ASAP.
Let's hear it. Who?
Huh? Chrome OS.
Oh, wow. Okay. Next slide. I was not for the recordings, right?
Yeah.
So, okay, so the version 2 now specifies that the doc supersedes, well, 1112, sorry, typo, for all content except for Appendix A. So 1112 stays normative for IGMPv1, and we make 1112 historic. So it's obvious, and then of course the explanation. So there are two explanation sections, kind of normative changes and then changes over 1112. I have that in the next slide. So pretty much the idea is in IGMP v2 and IGMP v3, we're referring to 1112. For IGMP v1, that stays the same. The fact that you're backward compatible with a historic version isn't hurting IGMP v2 and v3. But all the other documents going forward, we're checking what are you referring to? Are you really still talking about IGMP v1 in new RFC text? You shouldn't. So any new text that's written other than when it's referring to IGMP v1 would go to this new RFC, right? So that's basically what the text is trying to do, so that we have no changes in the status quo of what we're actually doing with our protocols, only the change in status quo of IGMPv1 being retired to historic. Okay. So, right, so then logistics and everything. So there's this template text block before 2009, that there is a text that the IETF doesn't have copyright over. I changed the references so that not everybody needs to remember what the numbers for our RFCs are. My favorite pet topic, packets with a multicast source address are not any form of IP packets. They're invalid, so I felt it was nice to add such a sentence. And then, yeah, so the explanatory text is now number 8 is new normative changes. So that is kind of, I think, most important for later ISG review, right? So that they're clear what normative changes are, which pretty much summarized what I was saying about IGMPv1. And then I was looking to other BIS documents, so and I moved all the existing explanation about the text changes into a section from an appendix. So, but there weren't really any significant changes here. Next slide. Right, and so that's pretty much it. So I very much hope that we're ready to adopt this. I think the 2 big issues last time are resolved with this. So yeah, Arthur would like to ask for adoption.
And we will do that in just a second. There were a couple of questions, comments on the list, particularly from Jim Stevens and Dino, since your last update, and they were involving.
Oh, since the last update.
Yeah, since the last update. Yeah, exactly. Just look at the list, and it's not a requirement to ask for adoption, of course, for the document to be perfect. But they wanted to know, what is a controlled federated network?
Okay.
There was a comment that ASM is still an important approach for intra-domain as well as overlays, and so they want to make sure that that's not.
Right. So. I think this was already in 01, and yeah, I'm happy to respond to that thread on the list. So there was in 11.12 the statement that IP multicast is the recommended or form of multicasting on the internet, right? And since then, people here in this working group, including myself, have authored this RFC. I forgot the number about interdomain ASM being retired. So now the explanatory section explains that the sentence was removed, right? So I didn't want to add additional text in terms of saying the importance in the main text, right? Because I still like the main text to be as unchanged as possible and really only crucial things. And so the fact in controlled networks, it's what we want, right? That is in section 9, right? So it's not in the main text, but that text is there and it refers to the RFC for retirement of interdomain ASM. So, and I'll also answer them on the list.
Okay. Any other comments for Torless? There is an adoption poll going on. Okay, again, for the notes, we have a strong show of adoption preference. We have 17 in favor and none against. And we will officially, 18 now, we will officially do so on the list. All right, we're good? All right. Louise, hold on just a second, let me get your presentation up. I keep losing connection to the server, so that's what's going on. Is it Louise or
Luis.
Louise?
Yeah.
Okay, all right. Okay, here we go. I think I got it.
Thank
Yeah.
you. So this is Luis from Telefonica. I will present this draft with the idea. What we are proposing here is a signaling-based configuration for supporting multiple upstream interfaces in IEMP MLD proxies.
Yeah, just keep
Okay.
it's kicking me out, but we'll keep giving it a go.
Okay. Well, I have done this draft together with Hitoshi Asada from NACT. So next, please.
Yeah, hold on a second. Okay, yep, I think we're good.
Okay, so a little bit of background on this. We have another draft describing this functionality of IEMP MLD proxy with multiple upstream interfaces. Where in this draft, there is the justification of that. So this is just a summary where the idea is to being able to get content simultaneously from more than one upstream interface. The current specification RFC 4605 that does only support one upstream interface. So we are proposing this new topic, let's say, of having more than one multiple upstream interfaces from the IGMP MLD proxy. Next, please. So in that scenario where we could have more than one upstream interface, there could be different selection mechanism of the upstream interface. One could be the static upstream interface configuration, so that it could be configured and based on and using one specific upstream interface based on the channel, on the subscriber, or any kind of priority. Then we could have another mechanism that would be based on a controller, being this element, the one configuring the proxy, that would be this SDN like control. And then in the middle, you can see what will be the scope of this draft. That would be the definition of an automatic upstream interface selection based on a kind of signaling mechanism. So this is what we will propose, and is based on the stations being defined in RFC 9279. Next, please. So the motivation, what we intend to do with this. So essentially to allow the host to express their preferences to the proxy regarding the interface to be used, and also if the host requires a robust reception of the stream so that the content could be delivered simultaneously from more than one upstream interface. And essentially to signal what is the upstream interface of the choice for the host for receiving the content. And also another target of this will be to allow the host to know what is the the upstream interface that is being used by the proxy to deliver the traffic. Next, please. So we have here two aspects to be considered. First one will be the policies defining the proxy for selecting the upstream interface. And this will be common for any kind of mechanism, the SDN-like mechanism, the signaling mechanism, and so on and so forth. So it will be common to all of them. And essentially, it's, the objective here will be to consider policies for either selecting based on the channel, based on the subscriber, based on the user itself, I mean, the host itself based on the source IP, and so on and so forth. But again, this will be common. This first part will be common. And then the second part will be particular to this draft, which are the different signaling situations of scenarios that we are trying to identify as valuable for the host. That would be first, the state retrieval per upstream interface. So to get knowledge, what are the upstream interfaces that the proxy is using, and what are the contents and sources that are being, let's say, retrieved from any of the upstream interfaces. Also, the possibility of getting the content from more than one upstream interface for robust reception of the content. And finally, also the way of informing the host where is the upstream interface being used, so such that the host can assess that is according to the request. Next, please.
Quick question.
Okay. So when you say that, yeah, this is Stig, when you say that you join on both interfaces, don't you get duplication, or are you saying that you will only receive, you will kind of join on both, but only forward for one of them at a time? Yeah, or? that's right. So Okay. the proxy should be in charge of
eliminating replication of the data. Okay. So next, please. So this is the signaling logic, the three different scenarios. In the first case, would represent the signaling for retrieving for the state retrieval from the proxy, so in such a way that the host can get informed what are the different upstream interfaces available, and also what is the content and the sources for each of the upstream interfaces. This is, well, did make use of those, the proposed extensions, the report extension from the host to the proxy for requesting the state retrieval, and the query extension from the proxy to the host for informing about what are the upstream interfaces and what are the channels and the sources per upstream interface. The second case in the middle would be essentially for the host to request a specific content from one source or multiple sources, as usual, but indicating the upstream interface of that the host desires for getting this content. Also, through this extension, the host will be able to signal if it wants a robust reception, so using more than one upstream interface. And the latest one, the one that you can see on your right, would be from the proxy to the host, just to let's say in the conventional reporting from the proxy that the contents that are being subscribed by the host, also to inform about the upstream interface that is being used for delivering that content. So we will go now through the different extensions quickly, for showing you what we are having in mind. So next, please. Yeah, regarding the first extension, that would be for soliciting the state retrieval per upstream interface from the host to the proxy. So here what we are detailing is just what could be the proposed extensions, but take into account that this will be augmented, or would be basically we are extending here a report message. So we have also the information of the report message that is not reflected here, not in the draft, but I mean, we will leverage also in that other information in the, let's say, conventional message. So basically for this state retrieval, we simply, let's say, code the need of having the retrieval and no more than that. So it would be essentially these two fields, the discovery request type and the discovery request length. After submitting the draft, we, the authors, were discussing, and probably discovery could be a misleading term. So our proposal is to change in the new version to a state retrieval, for making it much more evident that what we want to have is not a discovery of all the sources or the contents where the proxy could be connected, but just simply what the proxy is being receiving in each of the upstream interfaces. Next, please. This will be the other extension for the report message. Here, what we are trying to specify is how to request the channel and the source from one or more of the upstream interfaces. Because if we have if we want to enable the robust reception, we also need to signal if we want the host wants to receive from more than one upstream interfaces. So we have the basic encoding of the extension that is the one that you can see on your left, and then the details of what would be the kind of information that would be part of the value of this extension. So probably cannot be seen with, it's not so big, but essentially what we are putting in the value of the extension will be an index of the multicast address record for that we want to get. Also indication if we want just getting it from one upstream interface or more than one upstream interface. In case of receiving for more than one upstream interface, the number of simultaneous interfaces, and then the list of those interfaces. So here this message will come after the host getting knowledge of what are the different upstream interfaces, so that the host can signal what would be the desirable upstream interfaces for the multicast address that is in the main part of the report message. And yeah, and finally, basically that. So what is the multicast address that we want to get, and from where upstream interfaces? Next, please. This extension is for the query message, for reporting, I mean, for providing the state retrieval towards the host, right? Yeah. So essentially what we are informing here is for each of the source addresses that are in the main part of the query message, what are the different upstream interfaces that are providing that multicast address. Sorry, that source address. And again, here we add the list of some other fields like the list of upstream interfaces for essentially providing the information of the upstream interfaces associated to the source address and to the multicast address that is in the query message. Next, please. Next, please. And the final station that would be for providing the information to the host of what are the upstream interfaces that are being used for the content that the host has already subscribed, would be essentially this format for the overall message, and the value will be similar to the one in the report message showed 2 slides ago. It will be the same format. It's not reflected here for clarity. So next, please. Essentially, as next step, we would like to collect feedback from the working group to understand if this makes sense for the working group, if it would be interesting and so on. We would like also to refine the proposed extensions, so we need to elaborate more on them to understand if they are consistent, correct typos, also substitute this discovery by state retrieval, and so on so far. We need also to extend the content to IEMP. We are by now covering simply MLD, and we need to deal with the include-exclude modes that in the report message that we didn't have time to think on that for this IETF meeting. So we will provide a new version, and for sure comments and views are more than welcome. Thank you.
Hi, Muhammad Golden Nokia. I just want to understand, and I have to say I didn't read the draft inside out. So basically, you want to build the tree on all the interfaces between same router. So if you have 2, 3 interfaces between 2 switches or router, you want to build a tree, but then you do not want to send the stream through all those interfaces because obviously it's going to get duplicated. Is that the purpose?
I don't think so.
Okay, sorry.
I mean, we depart from the idea that from the MLD proxy, we can get the content from different upstream interfaces. So we are the tree is already there. So we are just the proxies attached through different upstream interfaces to the multicast tree. So what we can get is different content maybe from the different parts of the tree. This is documented in the other draft, right? The use cases and so. You could have the same content, you could have different content. There could be the same identifier of the group, but from different providers. So different scenarios that we consider that require this extension in the proxy. So what we are doing essentially is to, for the host to indicate what would be the upstream interface that we want to use for getting a given content from for a certain source.
But that's what I'm saying. The content is coming on multiple interfaces because you have redundancy between 2 switches. Yeah. And because it's coming on multiple interfaces, you're going to get duplication eventually on the host.
Duplication would be on one case. You could also select without duplication because maybe it's the same identifier of the group, but from different providers. That could be a potential case.
But if it's different, again, I'm just trying to understand, if it's different provider, then it is different SG, so you would think that that should go to the receiver, right? No?
But the identifier of the G could be the same, for instance. Could be not necessarily the same multicast address. So the different multicast address could be even the same multicast address.
The source doesn't have to be the provider, it could be somewhere else.
Yeah.
The tree spans downstream.
Okay. Okay. And basically, like nothing like a lag or anything like that.
No.
Stig here. So I understand the general idea, I think, and it might be useful for, say, a user to choose, which provider do I want to receive from. But what you get from with this extension, you just get like some interface ID, right? I think. So how does the user know that, okay, ID 1 is the one I want to join? The user doesn't know the context.
Yeah, probably the host will require some kind of configuration for associating the identifier of the upstream to whatever service logic. Maybe the provider, maybe basically the provider, or I don't know, the preference for, I don't know, technology, whatever. So an additional logic will be for sure needed for associating that, because otherwise it's not relevant.
Right. Yeah. So I think it needs some more text, maybe explaining how you would use this. And I was also wondering though, what happens if different hosts select different interfaces, right? You have a LAN and two different hosts select different interfaces.
That is a very good question. So we need to think on that. Because my immediate response would be that, okay, you will get different replicas of the content probably. But let me think on that and we will come with some solution for that.
Yeah.
Thank you.
Do you want an adoption call or no?
Well, this is 0.0 version. Maybe we need more work on that.
Okay.
Thank you.
Thank you.
Okay, thank you. I know we did adoption call on several 0 versions.
Should we do it?
No, I don't. I think it needs
Okay.
a little bit more work.
All right.
Personally.
Waymo, you're up. Let's get this figured out.
Hello, everyone. Today I'm going to talk about the adaptive stability multicast. Next page. A multicast tree is big and sporadic in some network. So here we have an example multicast tree, which is from Ingress node PE1 through P1, and then onto the Ingress node, a bunch of Ingress node PEs. So for example, in this multicast tree, at node P1, the links on the tree scattered a big range of links from link number 4 to link number 5, and then from link 108 to 109, and then to 119. So if we encode a multicast tree using one single encoding method, normally this is not most efficient. So we propose a solution which encode each tree portion using a most efficient encoding method. So in this way, the encoding of a tree, I think, is most efficient in general. So here, each portion of a tree is the links from any node. In addition, a portion of a tree can be part of a link from a node. So here we give an example. From the link from node P1, those links separate a big range of links. So we split these links into two groups, pink group and the yellow group. And then we encode pink group, the link in the pink group using link number 1 encoding method, and then yellow group in another method, for example, using flexible bit stream. So in this way, we can achieve most efficient encodings, and then the overhead for multicast will be minimum. For example, encoding the tree in the figure occupies 23 bytes. If we use the other method, link number, flexible bit stream, and so on, that will take 33 bytes, 35 bytes, and 38 bytes, and so on. So we can see that using this solution, we can achieve much enhancements. So with this encoding, at the Ingress node, after receiving a packet from traffic source, Ingress node just encap the package with a header containing the tree encoded, and then the package will be delivered to the egress node along the tree, and then we don't have any states in the core of the network. So how do we encode each part of the tree? And then first, we look some basic encoding method first. Next page.
Want to take a question or not?
Yeah, we can take questions. Okay.
It's just a fundamental question. This is Dino. I'm trying to figure out, are you trying to optimize less bandwidth and re-encoding like an audio or video stream?
Well, that doesn't matter as required. If some people wanted to have a higher performance, reduce the overhead, and then maybe they can.
Is it like doing ideas that CATS has, computer-aware stuff? Because when you were explaining the whole thing, that's what I was thinking. And then you said it eliminates state. And I don't know if you meant S comma G state or routing state. And then I got confused.
Routing state, yeah. The routing, so compared to the traditional multicast, and then we have a tree in each of the network, right? Each node of network. So for this, this is stateless, means that we don't have a control states in the core of the network.
In the pink part and in the yellow part. There's no state.
Yeah, we don't have a tree in the core of the network, in the nodes of core of the network.
And how do you know where to send it? Send packets and replicate?
Yeah, we can go, you'll see details in the following slides. How do we achieve that without any states in the core of the network? So first, let's look at the basic encoding method. So one encoding method is using link number. So basically for the link from one node, we can just encoding the link using link number. In addition to that, so if the likes of that link have branches or links, and then we can have a pointer to those branches. So that's the basic idea. So here we give example for encoding the link in the pink cycle in the first picture. So here we're in those pink group, we have two links. So we have a field number of links. So that field is 2, indicate we have 2 links. And then for the link with the link number 4, we use link number directly. 4 means link number 4 from P1. And then the link number 4 is from P1 to P2. And then P2, we have number of links. So we have point to the links from P2. So that's for the encoding of link from P1 to P2. Similarly, for the link from P1 to P3. So that's the basic idea of encoding by link number. So another basic encoding is encoding links from a node using flexible bit strings. So here we give an example for encoding the link in the yellow cycle on the first figure. So those links is link number 108, link number 109, and then until link number 119. So each of these links on the tree will use 1 bit with value 1, indicate that that link is on the tree. So here we have a field called start bit field. So here the start bit field has value 108. That means that the first bit in the bit string is corresponding to link number 108. So the next bit will be next one, 199, 109, and so on. In addition to that, we have a size of the bit string. So here we have 2 means 2 bytes. 2 bytes means 16 bits. So the bit string, the length of bit string is 16 bits. So here we have bit string. So this bit string, first bit corresponding to link 108. So the next bit corresponds to link 109 and so on. So each of the bit with value 1 will indicate that that link is on the tree. So here we indicate that link 108, 109, and 119, those links are on the multicast tree. So that encodes the yellow cycle link. So next page.
Couple more questions.
Can I ask you, you want to finish?
Yeah, you can ask. Okay. Okay.
Real quick, I think.
I just got one clarifying.
Yeah, okay, go ahead. Yeah, okay.
So the top encoding is for G1 and the bottom coding is for G2.
Yes,
That's
yes.
what you say.
Yes.
So you have to store at least G state. No?
No states. Go the details
Then how
in
do
the
you know
first.
what the fan out to use for one flow versus another is?
Yeah, that's a good question. In the following slides, we have a special link called the split link. Those link is some kind of virtual link we can in that way. and then those also encoded in the tree. So in the following slide, I will show that.
I believe you. I'll wait for your explanation.
Yeah.
Hey, AC Linda, maybe you'll answer this too. So this application was, you're doing, like with the bit spring, you're doing part beer and part like a multicast tree in with a different mechanism with the indexes in the packet header, right? You're doing two different types, right? For different parts of the tree.
Yeah.
In the same, it's a hybrid tree.
Yeah, you have tree. That's right. Yes.
Okay.
Maybe different ways. Yes. Thank you.
And it could be better if you're not going to change any of the unicast routing protocols to support it. Like it could be better, but I still don't understand.
Well, I think about it in more details.
Yeah, I should ideally do that at the mic, but anyway, Stiger. Yeah, so to me it looks a lot like beer or like beer TE. With beer TE, you can do some similar things. I think, like say, like which links a router should forward out and so on. But yeah, I think if you know beer, and it's basically kind of like that as I understand it, where the state is in the packet, you can say, instead of in each router.
Like switch. Okay. Yeah, like switch. So this is just another encoding method, and then this is called a half flex bit string. So this is similar to the flex bit string. Only difference is that the first bit is fixed, only the first link number 1. So that's similar. And then the fourth basic method is that we call fixed bit string. That means that the first bit must be the fixed. So that's correspond to last link number 1 and the last link. So that's another ways. So next page. So here we're talking about how do we split the link from one node into multiple groups. So we use a special link called a split link. Well, this is some kind of virtual link. So for example, from P1, we have a bunch of links, and then we split it in 2 groups, yellow group and pink group. And then we use 2 split link or virtual link. And then from P1 to G1, 1 group, and then to G2, 2 group. And then the link from in the G1 group, and then we just use one of a method, for example, link number. So for the yellow group, and then we use another method, and then use the flexible bit string. And then this figure just show the encoding of those link from P2, use 2 different ways. Yellow in one way, and then pink, and then in link number another way. So next page. So this is the whole encoding of the whole trace. And then for each part, we can use a different method. For example, from ingress to P1, we use link number. And then from P1 to the pink group and yellow group, and then we use split link. That's like some kind of virtual link. And then we encode the pink, use the link number, and use yellow group, use a flexible bit string, and so on. So we can have a whole encoding. So each portion of the tree use different ways, and then we can achieve most efficient. For example, encoding this tree, we take 23 bytes. So in any other method, we'll take 30 more bytes. So this is the most efficient in general. So next page. So in addition to that, each node have a label table. So this label table just contain the link numbers for the link attached to the node. And then this table will contain link number, the type of link, and then the IP address of next hop node. For example, for link number 4 is from link from P1 to P2, and then this link is point to point, and then the next hop address will be P2's IP address. And then use this link number, we can get the next hop address. And then for the special link, split link, virtual link, and then we have the link type. And then after a node decode this link number, this is virtual link, we need to do some special processing. So next page. So we also have a multicast routing header. So this header will contain the trees encoded. So basically, this header is very similar to segment routing header. And then the difference is that we contain the subtree. And then we have a point. This point will be pointed to the active subtree. And then when we do the processing, the header will not change. Only except for those point, that point will change to point to the subtree from my node. So that's all. So next page. So here we have behaviors for ingress node, transient node, and egress node. So this behavior will show how this solution will work. So on the ingress node, after receiving packet from traffic source, ingress nodes just duplicate package for each link, and then contain encap the package with the header. This header will contain the subtree from next hop that link, and then send the package to the next hop. So that's the, for example, here we only have one link from ingress node to P1, and then ingress node just have one package encapsulated with the header. So that header will contain the subtree from P1. And then the point, we can see that SL as a pointer points the head to start up subtree 20, and that's all. So next page. So this is the procedure on the transient node. So on the transient node, after transient node receive a package, so that package will contain the header. So that header will contain subtrees from that transient node. So the transient node, for each link from my transient node, so I duplicate the package for that link, and then just change the point to the subtree. That point will point to the links or subtrees from the next hop, and then deliver the package to the next hop. That's all. So in more details, because we have some special links such as split link, and virtual link. For that one, just do some special processing. Then that special processing is also simple. Just first update the point to subtree to point it to the group, right? And then we process the link in that group, such as pink group or yellow group. So in addition to that, for special link, for example, is to the egress node, and then we just set the pointer to tree to the 0, because for the egress node, we don't have any trees, and then that's all. For egress node, because egress node doesn't have any subtrees, and then we just decap the package and then send it to the multicast overlay. That's all. So that's roughly about this one, and then we can welcome comments. Next page.
The laptop has been packed, so I cannot raise hands through the system. Just one comment. I think there are several documents for this topic, just encoding the multicast tree into the data plan encapsulation. I noticed that there do have consider the balance of the complexity of the method and the efficiency. I noticed that your proposal is really, I think it is really an efficient way compared to, for example, just giving some pointer to the next segment, or just using bitstring. I think this one may be the most efficient way, or relatively more efficient. But I think it is really complex, and it is kind of combination of different approaches together to make the encoding really hard to understand or to pace for the device. So have you considered this aspect, and or do you consider to have a kind of analysis about the existing solutions in IETF about how we choose a better one for different scenarios?
Yeah, that's a good question. I think so. If we want more efficiency, and then this I know this is some kind of complex, because I have talked with offline with some people, and then they also mentioned that this is a bit complex. I think they should have some balance, right? If we want efficiency, and then you may need more complexity. So if this is bad, and also we needed to do, we may simplify this one in some way, right? For example, we may just select a couple basic method. For example, one link number and another one just one bit string, and then this will simplify a little bit.
This is Dino. I have one general comment and then a couple specific to your proposal. I'm seeing over like the last 3 to 5 years that IETF has this urge to put lots of complex instructions in data packets. This is like really a bad idea, and this trend has to change. So that's that one comment. Second comment, don't you care where packets come from? So is the virtual link used like an RPF check, or is it not?
No, this is this link without any checks, because so the link in the encode the
what if your downstream links now tend to be the S comma G tree around you has changed, and now it's an input link coming the other way? Can you change? Do you have to change is the question.
Yeah.
Because if you have to change, then you have to deal with RPF, and that's the problem Beer solved quite nicely. I mean, with the cost of changing a lot of things, but it solved that. So what are you going to do about that? That's pretty complicated.
Yeah, this one is about basic multicast, and then this one, the tree is generated by the controller. So there's other drafts in the PCE, whatever BGPU.
There's a controller.
Yeah, because the controller will get a join, leave, and then the controller will change the tree and send it to ingress. And
that's sad to hear. I have no other questions.
Thank you.
Yeah, we're a bit short on time here. So yeah, I have some concerns about this personally as well, but we don't have time to discuss much now. But you know, it's a bit controversial in the IETF as well. There was a buff, you know, on this overall topic, and it's also a question about whether beer, you know, is something that can be used. And so I think we need to, you know, we can have these details, but in the future, I think we need to go back and look more at requirements and see, you know, if people agree that this is a good way of doing things and whether we should do work in this area.
Okay, thank you.
Yeah.
Okay, thank you. So the rest of the meeting, Stig is the only chair. I'm involved in some of these other drafts. And last time, these guys, we had to rush through their slides, so this time they shouldn't have to. So let me just really quickly level set and kind of set the stage for these protocols that have been presented before. There's 2 protocol proposals that are seeking adoption. Again, I'm speaking as an author, and they're complementary protocols that allow for group allocation in a dynamic, decentralized way. Can you click to the next one? They presented before, but we haven't had a whole lot of time to discuss. So the primary problems with existing group allocation protocols such as MADCAP are, at least for some applications, such as Nate's marine application, which started this whole discussion, is that they're a single point of failure, collisions are possible at the Ethernet layer, and the configuration is more involved. If you look at the MADCAP document, it's quite lengthy and involved. And so again, for some applications, these problems block deployment. And so we're seeking some new ways of doing it. So there's a new draft that we're seeking adoption of, which is a problem statement draft that kind of discusses some of these problems. Next slide. We also have a draft that gets into the addressing problem, and maybe within some of your questions, we can get into that with their presentations. We need to get the address space from somewhere. It may be that we need to get that from the MADCAP group address. We can discuss that further. Each of the drafts specify what they need in their INS section. Next slide. So Nate's going to be presenting his proposal. He's presented this before, but hopefully we have more time to discuss on ZeroConf. It primarily is extending existing protocols. It's primarily focused on layer 2, although it doesn't have to be, but these ships are primarily layer 2 focused. If there needs to be inter-ship contact, then of course we'll need layer 3.
One question for me.
If it's a question about this draft, you can ask Nate, but go ahead.
No, when you say extends existing protocols, are you thinking of multicast DNS or?
Yes, exactly.
Okay. Yeah.
Next slide. And then Dino's been busy writing a new, instead of extending existing protocols, he's been writing his new lightweight protocol to do a similar thing. And he's going to share a demo on it today. And I think that's it. So from a procedure perspective, we are looking to hopefully have a problem statement draft adopted, a address related document adopted, and then these two solutions drafts adopted. They're complementary. And we think having two solutions is not a bad thing. It doesn't mean that they have to progress to the ISG, but we think having two solutions is a good thing. So with that, Nate, you're up.
Hey, good morning. Okay, so this is Zero Configuration Multicast Address Assignment. I'm Nate Carson with Garmin and National Marine Electronics Association. Mike did a great job introducing the topics here. I'm going to focus mostly on the first two documents where we talk about the problem statement and the group ID allocation. I think there's still some additional work I'd like to do on the MDNS-based algorithm, and we'll talk about that in a little bit here. So next slide. Okay, so we took the ZeroConf document that's out there right now, ZeroConf assignment-01, and we're going to split that into three separate documents. The first one is the problem statement. That includes the kind of the background on the marine use case, the use of multicast snooping, and some of the constraints that we have, and kind of describes that, and then distills those into a set of requirements, and then also some criteria that we can use for evaluating proposed solutions of ZeroConf address allocation algorithms in the future. So this, we believe, is ready for advancement. And then the second draft pulls out the discussion about the overlap of the server-based and host-based group ID allocation that's described in RFC 3307, and makes that a separate document to kind of allow for additional algorithms to be used and to avoid overlapping host-based and server-based algorithms. So there's some minor changes that I'll just discuss that I like to make to that, and then that should be ready for advancement. And I think, and then there's the existing ZeroConf document. I need to update that basically to pull out all the contents that went into the problem statement and group ID document, and then also to kind of reflect some of the latest things that we've learned from developing proof of concept. Next slide. So as you see on the top here, there's a 1. So any slide that has a 1 there is meant for the first document, the problem statement. And then the 2 is going to be for the group ID document, and 3 is specifically for the ZeroConf document. So the problems that we discussed is how to distribute the multicast traffic with a focus on efficiency, so that we're not sending that traffic over links that don't need it, but also because we have a mix of sensors that are high bandwidth and low bandwidth, we don't want the high bandwidth traffic to overwhelm the low bandwidth links. And so in order to accomplish that, we use multicast snooping. And because of the set of products that we have, the streams are, we can only differentiate them by the Ethernet destination address. That's because multicast snooping switches focus on the Ethernet address and not the IPv6 address. And also they don't support source-specific multicast. So we noticed also that there are address collisions at the Ethernet layer, and that's because you take, in order to get your IPv6 address onto Ethernet, you take the hex value 3333, and then you append the lowest 32 bits of your IPv6 address there. That lowest 32 bits is where you're going to have address collisions, because really any IPv6 address on the network, that 32 bits is the random section. The next highest 64 bits are the interface identifier, and that's what is used to differentiate the different IPv6 devices from each other. But then that randomness at the lowest one is what leads to those address collisions. We also need no single point of failure. So we don't run DHCP servers, for example, at least not a single one. And then we also cannot rely on user configuration. Next slide. So the desired solution is a decentralized zero configuration protocol for dynamically assigning those multicast addresses. Next slide. So the document then goes on to list all the requirements, and I basically copied them verbatim here. So it does not rely on a single point of failure, does not depend on user configuration. It coexists with other multicast address assignment protocols, whether they're MADCAP or whether we have two different host-based algorithms or however many in the future if there's other advancements that are needed. It supports operation on a single subnet, and it supports multiple applications on the same host. So we need to have multiple applications that don't have any way to communicate with each other be able to allocate their own addresses without stepping on each other. And then also it detects and resolves those address collisions. And an extreme case of that, which Dino does a good job describing in the GAP protocol document, is where a network is partitioned, where you're not able, devices are not able to talk to each other for a certain time. And then when they come back, that's where you have a potential for a large number of devices to have a address collisions kind of all simultaneously there. The red one there is not currently in the document, and I part of me thought that it was kind of captured in the supports operation on a single subnet, but it occurred to me it might be good to actually describe that there, because that was one of the things that was described or discussed. One of the options that was discussed in the Philadelphia meeting is, oh, just send all this stuff up to a server and have it, figure all this stuff out for you. So I think I would suggest adding that, unless people feel differently, but we can discuss that in a little bit. Next slide. And then these are kind of the extra credits. So assuming that we meet most or all of the, assuming a given algorithm or protocol meets most or all of the requirements, these are kind of some other things that we can apply to different problem spaces to help evaluate what's going to be the most appropriate solution there. So supporting operation across multiple subnets. Most boats are going to be a single subnet, and then when you start to get into the larger ships, those are going to be running multiple subnets on top of them. And then there's also talk about having, boats on the internet or even on local networks as they enter like a bay or a marina to have more automated docking procedures and stuff like that. So lots of interesting work being done there. Something that does not require significant changes to existing standards. That means that we can adopt it a lot faster or earlier than if we would have to wait for all of this to kind of be adopted and be implemented in operating systems and stuff like that. That uses the functionality commonly available on the variety of platforms. So we see differences in different embedded spaces, real-time OSs versus more server-based platforms like Linux and Windows. Uses capabilities commonly provided to unprivileged applications. So if we have to rely on kernel functionality, that's harder to provide on a variety of platforms. So having something that can be done in the application space on most platforms is desirable.
Sorry, you have just like 2 or 3 minutes left.
Okay. So we'll skip to the next slide. So it then goes on to describe IPv6 considerations on there and talks about the group ID ranges overlapping. Next slide. For IPv4 considerations, we kind of describe how the IPv4 address space is laid out, but I think the recommendation that we believe is that all new designs should use IPv6 because that was kind of better structured from the beginning to accommodate situations like this. Next slide. We also described 2 excluded solutions, and I'll skip over going into details there. Next slide. Then this gets into the second document. So this is a new dynamic multicast group ID registry in the IPv6 multicast address registry group. That's our proposed initial population of that registry table. Note there that the MADCAP allocation is reduced. The RFC 3307 basically assigns the full range of addresses there. And so we are shrinking that to a single entry. And that gives us room for developing zero-comp protocols. So the expectation would be as those zero-comp protocols are proposed, there would be an IONA consideration section that actually assigns those unassigned ranges. This also accounts for the fact that the solicited node multicast addresses are already being used in here, and so we would be colliding with those if we happen to be using that. And that's not currently reflected in any document. Next. There's kind of 3 to-dos here. One is to acknowledge that this updates 3307. I didn't list that here. Dave Thaler helped us kind of evaluate the use of MadCap and Microsoft products. So I want to acknowledge that. And then there's also this existing registry in the multicast address space registry. I've got a draft of the document that describes changes that we need to make to that registry to kind of reflect this work. But I think when I get those three in there, this will be ready for adoption. Next slide. And then the third document, I've been working on source code that has a proof of concept. So you can go to GitHub and get that there. And then there's also, I've been experimenting with different virtual machines and IP tables rules that will simulate that network partition and repair. And I can report on the results on that, hopefully in progress. Next slide. This also talks about some to-dos on that document. Next. That's it.
Yeah, so for the problem statement, you want us to possibly adopt that. So one question there is, sometimes we publish problem statements as like separate RFCs. Another approach could be for it to be like an appendix or something to some future solution. But you would prefer to publish the problem statement as a separate document.
Yeah, I think that makes sense because if we're going to look at separate or different solutions, having one document that's just the problem statement and the requirements and how we would evaluate those different solutions, and then those other, in this case, the MDNS based and the gap based, those will both reference that.
Right. Okay. Yeah. Yes, I think we can do. You're out of time, but we can do a quick adoption call for the problem statement.
Okay.
Well, of course, we would have to take it to the list, but let's just see what the interest is. Let's see. So I'm asking if we should adopt. I'll just call it a zero conf problem statement. Let's see. So I started a poll. Let's see what people think. Yeah, looks like we have pretty good interest, like 11 people support adoption so far and no one against. So so I'll do the adoption call on the list.
Okay. Yeah. What about the group ID document?
Sorry, which document
that
exactly?
Was number two.
Number two. Yeah, I think we'll take it to the list. We are well out of time, so.
Okay. Thanks.
But yeah, we can we can do an adoption call without checking in the room too. So let's consider that. Yeah. Okay. Yeah.
All right. Thank you.
Yeah.
Hi, I'm going to talk about GAP, and basically what we're going to do is we're going to show you a demo of a GAP application, and we did it last time at IETF over a set of Docker containers. So we had multicast that was native, but now we're going to show it over an overlay. And these are the folks that have been part of the testing effort. Also kudos to Nate, because he's been involved with GAP, and who else? Stig, of course, Stig, and Torlis has made some good comments too. So kudos to all those guys. Next. What is GAP? It's a new, totally decentralized multicast group allocation protocol. So any multicast application sources or receivers that want to be able to get a group address to talk on, they will run GAP in their systems. And the way I've implemented it, it runs as a library in the application. So there's no kernel changes. It runs in user space, and it's pretty lightweight. There's no central entity to allocate group addresses. This protocol does it for all the members. The group addresses are allocated and are guaranteed to be unique among all the GAP speakers within the GAP allocation range. And again, no zero configuration. Next. Design goals was to support both IPv4 and IPv6 group addresses. So when the allocations happen, they happen for both addresses, and the applications could use one or the other or both addresses to communicate if they wish to. It's easier to do that on an overlay because an overlay doesn't care if multicast is or is not on the underlay. Group addresses allocated will not collide, and we are layer 2 cognizant, so we make sure that they won't collide at layer 2 switches, MLD and IGMP snooping switches. So for IPv6, we make sure that the 32 bits are unique, and for IPv4, we make sure that the 23 bits are unique. Works on a single subnet as well as layer 3 infrastructure, including overlays, and that's what we're going to show today. Question?
Yeah, just a quick question with respect to the prior problem statement, right? So I remember this all being a great fun with the ships and cameras on ships, but obviously, yeah, if you have something like a list deployment, some controlled network with an overlay, this would be equally applicable, which I think you're talking about. Is that also those type of use cases captured in the problem statement, that kind of it is applicable to larger overlay networks? Because I think that would be good, right, if the world is aligned in that respect.
Well, I think Nate's proposal says it needs to run at layer 2, and if you have a layer 2 overlay, then it'll just work. And has it been specified? I don't know.
Well, at least as part of the problem statement, just, you know,
just an add, yeah, asked, right? Make so it extra clear that it can be
for overlay networks. It would be great to also have a solution, whether it's the same solution or another, it's different.
Yeah, very good point, Mike McBride. So yeah, in your problem statement, Nate, I'm pretty sure you mentioned the marine use case, which would be applicable for both solutions.
Next slide. Okay, so multicast source and receiver nodes participate in the GAP protocol. When the application starts up, it uses a group name, so all the user participants could rendezvous in the same session. So the group name basically is SHA-256 hashed into a group address, and then we either mask the lower 32 bits or 23 bits, depending if it's V6 or V4. And if the more than one group name hashes to the exact same 23 or 32 bits, then we send claim messages to say that there's been a collision, and then everybody, the collided group, the first arriver gets to win. The second arriver then has to hash to the group name +1 as an ASCII string. And we do that 4 times and then give up. Next. So we have a bunch of GAP applications. The GAP library is basically the entire protocol, pretty lightweight, so we can fit in quite easily. We built it in Python, and we, at the last IETF, we demonstrated this echo sender and echo receiver, and it was basically just send that text message there to the receivers, and they all joined this. The ERs joined all the same group based on that group name, and the sender sent to the same group based on that same group name. And then we had GapShark and various other utilities. But for this demo, next slide. For this demo, we built something called GapChat, which is basically a chat program that multicasts all its data. And all the participants type in GapChat group name, and they are able to chat back and forth. We put in a ping facility so you could see test reachability, and we're going to show you that now. By doing this over an overlay, we need multicast. And since we're doing this from people's homes behind residential gateways and NATs as well, we're also doing it on Starlink. So we have 2 nodes that are doing it over satellite as well. So we had to implement the signal-free multicast, which basically allows lists to be a multicast overlay when the underlay is unicast only. And then we have to all those boxes traverse NATs. In my Lispers.NET implementation, has a NAT traversal implementation. Next. This is what the demo is going to look like. The top 2 nodes are 2 VMs at AWS on terrestrial links. We have Dan Mitty at the bottom. He's on a terrestrial link residential. And Mike and myself are behind our Starlink Wi-Fi routers at our houses. And we're going to show that now.
I'd like to give you a demo of the GAP protocol over a Lisp overlay. Basically, we're going to show three technologies here. We're going to show GAP, the group address allocation protocol that allocates group addresses to applications, multicast applications dynamically. We're going to provide a multicast service using the Lisp overlay, and we're going to show that the Lisp parts of the Lisp overlay can run over a satellite network. We're going to show 5 nodes in this demo. We're going to show Dino MacBook and Mike Mac is going to be on the satellite link. We're going to have Dan Mini be on a residential terrestrial landline. And we're going to have 2 VMs in Amazon called XTR1 and XTR2 that are going to participate in the demo. So if we come over to these sets of windows, we have Dino MacBook here up in the upper left-hand corner. And we have Mike's MacBook here. These 2 are the satellite guys. And we have Dan's Mini right here. They're already joined to the group by using GapChat. GapChat is basically a multicast application that uses the Gap API to allocate addresses. When you start the application with a group name, it will hash into a group address that's being used. And we'll show you that in more detail in a second. Okay, so the idea here is we have all 3 that are part of the group that are already joined. And if we look at the RTR, we see the map cache in the Lisp RTR has the 3 members, Dino MacBook, Dan Mini, and Mike MacBook. It turns out that the group name Dino Group will hash into 224.94.0.236. And all of these nodes are also running the GAP protocol that runs on this well-known group, 224.0.170.170. Okay. The idea of the application is that it just broadcasts or sends messages to one another over the multicast group. So if we send this hello, we see that the other 2 nodes got it. The EID for Dino MacBook is 240.111. It was sent to the 236er group. And we see that Mike's MacBook received it. So this was sent over the satellite network to the RTR that's deployed in Amazon, and it replicated the multicast packet to Mike over the satellite and to Dan. Note that the group and the source are the same. Okay. Now what we're going to do is we're going to have these other 2 guys join from XTR1 and XTR2, which are 2 VMs. So starting up the GapChat group, we're going to start this guy up, and we're going to show that the join latency is pretty fast. So if we then again look at the RTR, we will see that XTR1 is now joined to the group. So we have now 4 members that are running. And let's say he just sends, hello, I am XTR1, just joining, and everybody should get that message. Okay, and we see that Dan got it, we see that Mike got it, and we see that Dino got it. Okay, let's just join one more. Okay, and let's say, hello, just got here, I'm a XTR2, and you can see that Dino got it, Mike got it, and Dan got it. And let's look at the other VM, and the other VM also got it. If we just look at the state again in the RTR, we'll just see now that we have 5 group members, 1, 2, 3, 4, and 5. Okay. Now what we implemented was a ping protocol in the application. So if one of these guys sends a ping, it'll just show that everybody has received the ping, and then they're all going to reply to the ping with a Pong message, and the Pong message is going to be multicast back to the group. So let's try that from Dino MacBook. Okay, so what happened here was we did the ping, and Dino MacBook sent the ping out to the 236 group. It's associated with Dino-group. And this was the sequence number for the ping. And what Dino got back was from a XTR2, the AWS VM, got a pong from it, got a pong from XTR1, got a pong from Mike, and one from Daniel. Now, since these pongs were multicasted, we see that all the other nodes have received the pong too and are displaying it. Okay. So basically, we're providing a multicast service here with the Lisp overlay, and that's allowing anybody to connect anywhere on the internet where they have connections to the internet underlay. And it could be satellite, it could be terrestrial, and they're all behind NAT devices, so the NAT traversal logic is being used here as well. Thank you for watching.
Questions?
Yeah, Atlas, yeah.
Yeah.
No, just go. Yeah. People.
So you said layer 2, so there is some form of list where you can.
No layer 2, all layer 3.
Is this all layer 3?
Yeah. So just for these two allocation protocols that we're working on, both GAP and the zero conf stuff Nate's doing, we're positioning them as complementary. So GAP is used as an address allocation protocol, either over layer 3 and therefore could work over layer 2. But Nate's is looking at layer 2 because he wants to optimize layer 2 switches.
And how do you get then from one, so the XDR is on each member's LAN, but it's a router.
Oh, so I think your question is where do you put the overlay nodes?
So how do you get through the kind of multicast, right? It's ASM multicast, right? So
yes,
right. So
there is no native multicast running or no protocols running whatsoever. And the XTRs, the Lisp encapsulators and decapsulators are co-located on the same systems where the GAP chat application is running, all over layer 3.
But they could also be on the LAN. So I can extend.
Last IETF, they were all in Docker containers on the same common LAN, and they were using native multicast through Docker. It was a single subnet, but it was native multicast.
Okay, my application sends something, it gets to the XTR is routing it over Lisp, right? Encapsulating it and sending it to the others,
Yeah.
right?
Okay, if you want to know how it works, do we have time?
No, I mean, we can take it offline. I mean, it's fine.
I mean, it's pretty simple. It's the fact that the application is sending from an EID means that Lisp takes control over the packet versus it going down through the kernel. And so when the ITR sees this SCOM-G packet from the application that's right on the same system as it, it does a lookup in the mapping system and then finds out what the replication list is. But since here it's complicated because the network is complicated, since here this XDR is sitting behind a NAT, he encapsulates all his packets to the RTR. So really all these XDRs have a single default route for unicast and for multicast to send it to the RTR. The RTR does the mapping system lookup and finds all those members, and then unicast replicates to all of them.
So the RTR becomes kind of like the Lisp RP, so to speak.
Yeah, but we don't have to make it work that way because we have a decentralized NAT function where we could actually replicate at the source to all of them as well. So choose your poison there. Do you have the hairpin or do you replicate close to the source?
Yeah, we're out of time, but
Okay.
yeah, thank you.
We're good?
Yeah.
All right. Thank you, guys. Appreciate your participation, and we'll see you on the list and in Prague.